Okay, so we're going to do this three-wire circuit question. And what we're going to try to find out, given the values that we have up here, is the voltage across load 1 and the voltage across load 2. All right, so let's add in the values that we are given. So R1, the resistance in the conductor here is, internal resistance of the conductor is going to be 0.01 ohms. Likewise with R3, 0.01 ohms. And through the neutral, R2 is going to be 0.2 ohms. So those values are given to us, and we're also given our load current. So through load 1, I'm going to just change up my color. Our current is going to be 3 amps through load 1 and 14 amps through load 2. All right, so I'm going to add in I'm going to, first of all, just give the current a direction. Because it's AC, it would be flipping back and forth, but we're just going to be looking at this at a snapshot in time. And so we'll say that our current at this snapshot is going clockwise. And so we'll give a direction here, here, and down at the bottom. So everything's going clockwise. All right. Now, if we have 3 amps going through load 1, that must mean we have 3 amps going through our conductor that feeds it. And if we have 14 amps going through load 2, we must have 14 amps going through that conductor, the outfeed. And the neutral, well, the neutral is going to carry the imbalance. So the imbalance of 14 and 3 would be 14 minus 3, 11 amps. Now we got to come up with the direction of current going through the neutral. And that's pretty easy to do. If we have 14 amps going to the left of the page at the bottom, and we have 3 amps going to the right of the page, or the screen, then those must equal. And so the 11 amps, or the current going through the neutral, is always going to be in the same direction as the smaller of the unbalanced loads. So the 3 amps, in this case, going to the right of our screen. Okay, so now having current and resistance, we're able to figure out what our voltage is going to be. So we simply use Ohm's law, E equals I times R. So that's going to give us 0.3 volts down there, 1.4 volts here, and on the neutral, 2.2 volts. All right, so now we got to figure out how these voltage drops on our resistors affects our loads. So Kirchhoff's law states that if we have a 120 volt source between these 2 points here, the voltage drops need to equal 120 volts coming back. So we're going to trace our path. It doesn't matter what path we take. It has to equal whatever the source was. So our source is 120. If we have a 0.3 volt drop there, we have a 2.2 volt rise on our neutral. And the reason it's a rise is because the current at this snapshot in time is traveling in the opposite direction as our Kirchhoff voltage loop here. So our trace from this point to that point. And because it's going in the opposite direction, it acts like a rise. And so we would have 120 volts minus 0.3 volts, which brings us to 119.7. So 120 minus 0.3. But then you add the 2.2 volts, and that's going to give us 121.9 volts. So that's what we're going to have at that load. 121.9 volts. Down here between this point and this point, that's also going to be 120 volts, and that must also equal, or tracing around our Kirchhoff's voltage loop here. So in this case, we're going to have a 2.2 volt drop because our loop here is going in the same direction as our current. So whenever that happens, it's a drop. So we got 120 minus 2.2, and then minus 1.4 through that conductor. And that's going to give us 116.4 volts. Okay, so this is going to be our answer to the voltage across our loads in this unbalanced three-wire circuit. Now, the second part of this question is, what is our current going to be, our line current going to be if the neutral breaks? All right, so to figure that out, what we got to do is we got to know the resistance of these loads when the neutral is intact. So I'm going to switch over my color to green. Now keep in mind that the resistance never changes. It's fixed, it's engineered into the load itself. And so unless it's like a rheostat or a potentiometer or something, that resistance does not change. So let's figure out the resistance of our loads. And we also got to remember that it's important to remember that current is the byproduct of our voltage and our voltage going in, our supply, and the resistance of that circuit. All right, so we need to know the resistance if we're going to figure out what the line current is after our neutral breaks. All right, so we can again do that using Ohm's law. R equals E over I. 121.9 divided by 3 is going to be 40.6 ohms. And down below, 116.4 divided by 14 is going to be 8.31 ohms. And you can see how unbalanced this particular three-wire circuit is. And we're going to see the ill effects of it. Okay, so now keeping in mind that those resistances do not change, we'll simulate the fact that the neutral is taken out of the equation. It's broken at some point, it becomes disconnected. And so now what we're dealing with is, rather than 102 portions of 120 volts, we're dealing with 240 volts. So I'm going to redraw this circuit quick as if the neutral was never there. So now we have a 240 volt source with a bit of line resistance. Our load 1, actually we'll draw it in like it was before. Load 2, bit of line resistance, and there we go. So again, our resistances do not change. So let's go that color there. So 0.1 ohms. Our resistance on load 1 was 40.6 ohms. On load 2, 8.31. And our line resistance was 0.1. So now what we're dealing with here is essentially a simple series circuit. So we have our E total, or R total can be calculated by simply adding up all the resistors. So 0.1 plus 40.6 plus 8.31 plus 0.1 would give us a total resistance of 49.11 ohms. Now using Ohm's law again in a classic formation, I equals E over R, we can figure out our current, and our line current for this particular circuit is going to be 4.88 amps. All right, and in a lot of cases, I'll just go over this real quick. In a lot of cases, they're going to ask for what is the new voltage on our particular load. So let's just go ahead and solve that, even though it's not part of the what they're looking for an answer. So we just multiply our resistances by 4.88 amps. And end up with 198 volts on load 1. And 8.31 times 4.88. End up with 40.6 volts. Now there's a couple rounding errors for sure. Well, actually we got the drops in our line resistance as well, in our conductors as well. So it's not going to equal 240 volts, these two, quite yet. But either way, what you can see here is the imbalance of voltages, the voltage drops on our load, which is what we would never want. We want to maintain that consistent 120 volts or that on our loads. That's what most loads are designed for. And as you can see, now that the neutral is gone, one load is receiving almost 200 volts, the other one's only receiving 40 volts, and that's going to have a very ill effect on whatever we have plugged in to that circuit.